Okay, so in this video we're going to go over half-life. Now, half-life is the time it takes for a substance to decay. So a lot of substances just naturally decay into other elements or just decrease by half. So the time it takes for half the substance to decay or decrease. So if I have like carbon-12, carbon-12 has a half-life of about 5,000 years, somewhere around there. So it takes 5,000 years for half of that substance to decay. So if I had 100 grams of a substance and its half-life is 5,000 years, after 5,000 years, so after one half-life, only 50% of this would remain as carbon-12. After two half-lives, this would reduce by half again. So half of 50 would be 25. If I had three half-lives go by, I would have half of the 25 remaining, which would be 12.5 grams, and then so on and so forth. So half-life is the amount of time it takes for a substance to decay or decrease by one half. So with a zero-order reaction, the half-life decreases with decreasing concentrations. So as my concentration decreases, so does the time it takes for half of that substance to decrease. So the first half-life, after so much time, so about 30 seconds or so, half of the substance disappeared or decayed. So right here, it takes me about 30 seconds for half of it. Well, once we get to that point, the concentration is different now. So then it only takes not another 30 seconds, but about half of that for half of that substance to decay. And then it just keeps going down and down as I decrease my concentrations. So the half-life, which we use a T1/2 to represent a half-life, is equal to the concentration, the initial concentration, divided by 2 times the K constant. And most of these equations are given to you. All right, so for a first order reaction, the half-life is constant and does not depend on the concentration. So right here, my half-life is, let's say, about 15 seconds. Well, in about another 15 seconds, so about 30 seconds, I have two half-lives that have passed, and I should only have about 25% of whatever I started with. Another half-life goes by in the same amount of time, and then half of that substance decreases. So to get the half-life of a first-order reaction, we're going to take 0.693 and divide it by K. Now, with a second-order reaction, half-life is not constant, and it will increase with decreasing concentrations. So basically, as my concentration gets lower and lower, the half-life increases, so the time it takes for it to decay or disappear or decrease would be longer and longer. So for the half-life in this case, I would take 1 divided by K times the initial concentration to figure out what the half-life is here. And I know the first order and the second order half-life equations are given to you in the AP reference sheet. All right, so let's look at an example. A first order reaction is 38.5% complete in 480 seconds. Okay, so calculate the rate constant, so calculate K, calculate the value of the half-life. So what is the half-life here? And how long is it going to take for the reaction to go to get to the point where we have 25% remaining, 75% remaining, and 95% remaining? All right, so the first thing here, I want to calculate the rate constant. Well, if I look at the half-life equation, which you just saw, for the first order, it's 0.693 divided by K. Well, I can't calculate K without the half-life. But I do have another equation that involves first order reactions. And it's this. The ln, the natural log of the concentration at whatever time, minus the natural log of the concentration at, or the initial concentration, is equal to the negative K multiplied by T. This is another equation that's given to you on the reference sheet. So we're going to have to use both of these equations to solve the entire problem. All right, so when I'm looking at this, it says that the reaction goes and is 38.5% complete in 480 seconds. So at 480 seconds, I have decreased my amount by 38.5%. Well, the good thing is here with a percentage, we can assume we started with 100. Let's just assume our initial concentration is equal to 100. Because it's a percentage, I can do that. So we're going to assume the initial concentration is 100. Well, 38.5% complete means that at that time, at 480 seconds, I only have 61.5 grams. So if I start with 100 and I go until it's 38.5% complete, I can take 100 minus 38.5. That means at 480 seconds, I have 61.5 moles per liter. And I'm doing that because I'm assuming that I'm starting with 100. It goes until it's 38.5% complete, which means at 480 seconds, I have 61.5 moles per liter. So I have my concentration at 480 seconds. I have my initial concentration. I have the time, it's just 480 seconds. I can simply plug in everything and solve for K. So my natural log of the concentration at the time was 61.5 minus the natural log of 100 minus K, which I don't know, and my time is 480 seconds. All right, so let's plug this in. I'm going to get negative 4.86 here. All right, so to get K by itself, I have a negative 1 here too, so I'm going to divide, by, not by 480, but negative 480. So K here is equal to 0.001. And for first order, it should be seconds to the negative 1. All right, so I have K now. So now let's go ahead and calculate the half-life. Okay, so the half-life is equal to 0.693 divided by K. So my half-life is equal to 0.693 divided by K, which is 0.001. So just plug it in and get your half-life, and we'll get 693 seconds. So that means that it takes 693 seconds for half of the substance to decay. So if I started with 100 grams and 693 seconds, I would only have 50 grams. If 2 half-lives have gone by, so about 1358 seconds, I would only have 20 grams because that's half of 50. All right, so let's look at the rest of it. It says, how long will it take for the reaction to get to the point when you have 25% remaining, 75%, and 95%. Okay, so I know that my half-life is equal to 693 seconds. Well, to get to the point where I have 25% remaining, I can really just think about that. I don't have to plug it into an equation. Because I know after one half-life, I'll have 50%. After two half-lives, I will have half of 50, which would be 25%. Well, if 25% is remaining, that means two half-lives have gone by. So the time it would take for that to happen would be two half-lives. One half-life would be 693. Another half-life would just be another 693 seconds. So it would be 1358 seconds. I can just simply think about that one. All right, let's look at 75% remaining. So I have 75% remaining. If I'm going to do this with math, I can use this equation right here. Well, if 75% remains, that means that I have a concentration of 75. I can assume it's 100, and then my initial concentration would be 100. Well, I'm solving for the time. I have K. I can use this equation to do it. So the natural log of 75, because 75% remains, so at some time, some amount of time has gone by, 75% remains. Oh, minus. I'm going to subtract the natural log of the initial concentration, which I'm going to assume is 100. Set that equal to negative K, which is 0.001, multiplied by the time, which I'm solving for. I want to know how long it takes me to get to a concentration of 75. All right, so if I plug it in, I'm going to get negative 0.287 is equal to negative 0.001 times T. Divide both sides by negative 0.001. My time would be 288 seconds. So it takes 288 seconds for 75% of my substance to remain. All right, so let's look at the rest of it, 95%. Okay, so 95% remains, so at a certain amount of time, 95% still remains, so the concentration at that time can be 90, the initial can be 100. So the natural log of 95 minus the natural log of 100 is equal to negative 0.001 K multiplied by some time. So if I plug this in, I'm going to get negative 0.0512 divide both sides by that. And then T would be 51.4 seconds here. Okay, so when we're looking at half-life problem, you are given equations to figure out the half-life, but if you're looking for concentration, you would need to use the straight line equations, which are provided for you on the reference sheet. So if you're looking for a concentration at a certain time, or the time when a concentration is a certain amount, you can use those straight line equations.